This lecture is about the rationale method, and we're going to talk just briefly about the backgrounds and uses, and then I'll go into the methodology itself and, and touch on a few things about that. First of all, the rationale method is a peak flow runoff method. And so basically, if you think of the entire hydrograph, what the rationale method does is it estimates what this peak flow will be. It's very similar to the USGS regression equation method, which some of you may not be familiar with, but essentially what the USGS has for every state in the country, they have, based on basin characteristics and type of watershed, they can estimate the various peak flows for anywhere in the tributary or anywhere in the state based on the size of the drainage area and other basin characteristics. So they estimate such things as the 2-year, 5-year, 10-year, 50-year, 100-year, 500-year peak flow. Now, the rationale method has been around a long time. It's used since the 19th century, and it is the most widely used peak runoff method in urban hydrology, especially for storm sewer design. Now, it's a very simplified method. It's not as rigorous as modeling methods that would be more physically based or something like the unit hydrograph. But for small watersheds, it can be effective. This, in essence, is the rationale method model. It has the peak flow as equal to a runoff coefficient C times the average rainfall intensity, either in inches per hour or millimeters per hour, taken for the appropriate frequency, risk value that you would have. And that intensity would match whatever the time of concentration of the watershed would be. Because one of the inherent assumptions is in the the rationale method is you're allowing it to rain until the most hydraulically remote point is reporting in, so to speak. It's when that water droplet from the hydraulically most remote point gets to the outlet where you're modeling the Q, that is the time of concentration. And so we're assuming that the rain of some intensity is occurring up until that point. So you would select your duration for your intensity of rain based on whatever that time of concentration is. The last component there is the area, which if we're in English units, it's acres. If it's SI, it's kilometers squared. The K value is just a coefficient for units, and so if it's English, it's a 1. If it's SI, it's 0.28. Now, let's talk about the conceptual idea of the rationale method. And this gets into where I was talking about selecting the duration of the rainfall that you select is equal to the time of concentration, because it's assuming that the entire catchment area is contributing to runoff, in which case the duration of the storm must equal or exceed the time of concentration of the catchment. So estimating that time of concentration is going to be important. You know how to do that. You received lectures on that, various methods, and we learned the lag method, which is an equation. We also had the various sum of the velocities divided into the length, right? So the length of distance divided by the velocity gave me a time of each each watershed component. So if you had grass flowing into wooded area into a channel, you would sum up those various lengths or the times over those various lengths, and you'd come up with a total time of concentration. So we have to be able to do that. You can look back at previous lectures where I've covered that in terms of getting the time of concentration. The rainfall is distributed uniformly over the catchment area. This is a very similar assumption that we have for the unit hydrograph, and that all catchment losses are incorporated into the runoff coefficient. So we really don't worry about infiltration abstraction. All that gets caught up in the value of the coefficient that's in the equation. Again, we've got K CIA. So that coefficient for the runoff coefficient for the watershed. Excuse me. The idea of the rational method is that the rain keeps falling over the entire watershed until all parts of the watershed are contributing. At that point, the runoff becomes constant. So you can almost think of it like a S hydrograph, really, where you've got some flow, and then if you allow it to just continue to rain, you come up with an equilibrium value, a constant value. Well, this is not the S hydrograph, but we're in essence the rational method just assumes you're going to allow it to rain until you get a constant runoff. By the very nature of these assumptions, you only use this on small catchments. Less than 200 acres is a kind of a rule of thumb. And so, because we assume uniform rainfall and then it rains at that uniform rainfall amount all the way until the hydraulically most remote point is contributing to the runoff, that really kind of lends itself to this assumption, or I'm sorry, the forcing us into small catchments to make those assumptions more valid. And you're selecting the C. This is not quite the same, obviously, as the curve number, but similar. You're going to look at the type of the surface, the character, and then based on the return period, you're going to pick a value of C. And so if I'm looking to have a 100-year return period or a 1% annual exceedance probability, and I've got, some sort of grass area, and, it defines here poor condition, fair condition, good condition, I would look at that and I would come up with a value of C. And it's going to vary from 0 to 1, right? And so the lower the number, the lower the value, the lower the peak runoff. And so if you can see up here with my asphalt developed conditions, I've got very high values of C, where if I'm over here in cultivated land, I've got much lower values of C. If I want to select that rainfall intensity, I'm going to determine the time of concentration, as we said, and we've got the lag method and then the upland velocity method are the two that I've introduced into this course. And then I'm going to determine what frequency you want to design for. And then I'm going to go and find some intensity duration frequency relation. Again, for the most part, I'm using NOAA Atlas 14, and I got a slide here in a second that'll talk about that. If you're in Illinois or the Midwest, where the Illinois State Water Survey's Bulletin 71, now they've got a new Bulletin 73 out, covers the area, you can get relationships there, but you're going to use those to come up with an intensity value that's going to match your time of concentration, and we'll talk more about that in a second. Again, just to remind you, the time of concentration, we've got the lag equation, and we've got those upland velocity equations again. These come in various forms, but again, it's on the curve number, the storage of that. I'm sorry, the average slope of the watershed, the length. You go through those various types of watershed characteristics to come up with your time of concentration. You can go to this website here and you can see, where we've got Bulletin, we got NOAA Atlas 14, and all the sites in blue are where NOAA Atlas 14 exists. If you go to one of the non-NOAA Atlas 14 sites, the Pacific Northwest, you can click on those states and figure out the appropriate publications to use. But if you click on, this is Illinois, if I click on Illinois, I can get results from that, and I can get the table. Again, you've seen this. Now, one thing I want to caution you on is make sure that here I've got precipitation depth selected here. You can click this and get intensity, which is what I would recommend for this. Get the intensity. And then here is the depth, but I could have also generated a table of intensity. Because that's what we're going to use. That I value in the equation is going to be inches per hour. Now, because the time of concentration likely is not going to fall on one of the values that are in the table. Again, here's my duration: 5 minute, 10 minute, 15, etc. Let's say that you had a time of concentration that was at 8 minutes. Well, it's between 5 and 10. So you need to interpolate between the two. And so you can see on this plot here, I can come up with an interpolation. Here I've plotted inches per hour. And so I could get a value for whatever frequency of storm I'm looking at. I can get a value between there to come up with an estimate of the 8-minute intensity for that rainstorm.